cover it next Wednesday also. So for those of you watching the recording, we've got today we're going to review sections 4.1 and 5.1 a little bit, and then cover 5.2 and 5.3. All right, so I'm just going to go ahead and flip the screen, and then we are going to go from there. All right, so section 4. Well, first of all, remember we're talking about polynomial functions. Right, and so polynomial functions, remember, are functions that are kind of in this form: f of x equals, and I'm just going to write this as addition, subtraction problems, addition, subtraction of powers of x. Right, so you just have a bunch of powers of x added or subtracted together, and so that's what you're talking about with a polynomial function. First degree polynomial functions are linear functions. That's what we covered in section 4.1. And those functions are in the form f of x equals mx plus b. Right, and remember that's just the slope-intercept form of a line, and that all graphs of linear functions are lines. So all graphs are lines. And if you have a function that's in f of x equals mx plus b form, then you could graph the line easy enough. So like f of x equals 2/3 x minus 1 is a line. Right, that's a linear function. It's a line with a slope of 2/3 and a y-intercept at 0, -1. And so you could make a decent sketch of that graph just knowing those two things. Right, so that the y-intercepts here at 0, -1, and then you know that the slope is 2/3. Remember that the slope being 2/3, that's just the rise over the run. And so that means you're going to go, on this graph, you're going to go up 2, 1, 2, and you're going to go over 3, 1, 2, 3. Right, we go up 2 and over 3, and then we get another point on the graph over here at 3, 1, and then we've got enough to sketch this graph. Like that. So, so the key here, linear functions, remember, are first-degree polynomial functions. These are first-degree polynomial functions, and they typically, or they can be written in this form: f of x equals mx plus b, which is the slope-intercept form, and that the graphs are all lines. Right, whenever you get a linear function like that. All right. So now, second degree polynomial functions. So that was first degree in the last page. Second degree polynomial functions are called quadratic functions. That's what we covered back in section 5.1. And the general form for these is f of x equals ax squared plus bx plus c. What we saw was that the graphs for these kinds of functions, that the graphs are parabolas. And that if that leading coefficient a is greater than 0, if it's positive, then the parabola opens up. And if a is negative, then the parabola opens down. Okay, and so we talked about two different forms for these as far as graphing them. We've talked about that if you have a function that looks like this, f of x equals 2 times x, let's say, plus 3 squared minus 4, like that, that because we could identify the shifts of the graph, that we could find the vertex by the way this equation was written. that this graph shifted left 3 because of the x plus 3 and down 4. And because of those two things, we could write down the vertex for this parabola. And the vertex we've got was at -3, -4. We also note because the 2 is positive that the parabola opens up. So we know that it opens up like that. And so, I wanted you to write the vertex down, the axis of symmetry. So let's see, I'm going to make a sketch of the graph over here. So -3, -4 is right here. We know that the axis of symmetry is a vertical line that goes through that vertex. This is the axis of symmetry right here. So we know that the graph is symmetric around that line. And so I'm going to write down the axis is the line x equals -3, right? That's this vertical line right here. And then we also, what I would want you to be able to do is write down the x-intercepts and the y-intercept for a quadratic function. And we talked about doing that last week. So this is all going back over stuff that we covered last week. The x-intercept, remember you set y equal to 0 in the equation for the function. And you solve it for x. So I would add 4. I divide by 2, like that, to get the x plus 3 squared by itself. And then I take the square root of both sides of the equation. Don't forget the plus or minus there. And then I subtract 3 to solve for x. And so I get the x-intercepts to be at these points, these irrational numbers, because it's got a square root in it. -3 plus or minus the square root of 2. There's 2 of them there. We could use decimal approximations there if we wanted to kind of approximate where those were. Square root of 2 is approximately, you could use a calculator there, but it's approximately 1.4. And so these intercepts are really at -3 plus or minus about 1.4. And so that would give us -4.4 and -3 plus 1.4, which is -1.6. And I put a little dot over the equal sign just to say that it's approximate there. And so if you needed to approximate these, you get one intercept right there and another one right about there, and they should be symmetric around that axis of symmetry right there. So those are the x-intercepts. And then the y-intercept is always easier to find. You're setting x equal to 0, and so you get in the equation y equals 2 times 0 plus 3 squared minus 4. So you get y equals 2 times 9 minus 4, which is 14. And so our y-intercept's at 0, 14, which is kind of off my graph a little bit there because it's a pretty big number. So you get a graph that looks something like this. It's a relatively narrow parabola, and it kind of looks like this. Remember that this vertex point here for a parabola that opens up like this one does means that the vertex represents a minimum y value. It's the smallest y value that you get. And so the minimum y value there would be -4. Because that's the y coordinate of the vertex, right? The vertex is at -3, -4, like that. All right, so we talked about this is going back over things that we've done before, but it's been a while now since it was before the exam, and so it's been a week since we've talked about this. Actually, more like 9 days. So, all right, so. So now continuing with quadratic functions, if we have a function that's like this, let's say we have -3x squared minus 12x. And let's say that this is plus 5. Okay, like that. All right, so this is a parabola. This is a quadratic. It's a second degree polynomial function. That 3 is negative, and so that means that this parabola opens down. And the problem is we cannot identify the shifts on this graph, so we complete the square. And this is something we talked about last week. Complete the square to identify shifts. And to find the vertex. All right, so what we to do that, what we did is we moved over that 5. So the 5 kind of slides over like that. We leave a space, and then we factor out the -3 from those first 2 terms. And so that changes the sign, and we've got -3 times x squared plus 4x. The plus 5, remember, just kind of sits out there all lonely by itself. It doesn't have anything to do with that factor, and whenever you factor out that leading coefficient, you don't mess with that constant. It just sits over there by itself. All right, and now we complete the square. We take half that middle coefficient. So 4 times 1/2 is 2, and we square it and we get 4. And so 4 is the constant that I add in inside those parentheses there. So I'm going to write the whole expression down again, but in a different color. I'm going to put in here plus 4 right here. And then don't forget, if you have a coefficient sitting out here in front of the parentheses, you have to multiply that by what you've added on the inside. And so I've really subtracted 12. And so when you add that constant in, you must also do the opposite right here. Remember, this has always got to be the opposite because you're trying to offset what you just did. So because you're really not trying to change the equation at all. You're not allowed to change the equation. So you subtracted 12, so over here you would add 12. And so f of x would be equal to -3. That trinomial inside the parentheses always factors as the square of a binomial, and it's the first term, the square root of the first term, the sine of the second term, and the square root of the last term. So it factors as x plus 2 squared, and then plus 17 on the outside. And so in that form, that's the whole idea, remember, is to take this function that we started with and rewrite it using completing the square so that we could now identify the shifts of the graph and we could write down the vertex. So that's what we did. And so the vertex for this particular parabola would be at -2, positive 17. Shift left 2 and up 17. So the vertex is at -2, 17. The axis of symmetry is always x equals the x coordinate of the vertex. So that's x equals -2. The x-intercepts are not particularly pleasant to find on this problem. But if you set y equal to 0 in that last equation, you're going to get a yucky form here. And so if you subtract 17, we can use the square root method to do this, but it's going to be a yucky form at the end. And then divide by -3. So 17/3 equals x plus 2 squared. And then you take the square root of both sides of the equation. You get plus or minus, see, and this is where it's yucky. You get this nasty fraction, 17/3 under the radical equals x plus 2. In WebAssign, they will always rationalize that. So they'll multiply the square root of 17/3 by the square root of 3 over the square root of 3. That's multiplication right there. And when they do that, In the denominator, they get the square root of 3 over this times the square root of 3, which is the square root of 9, which is 3, right? So there's no longer a radical in the denominator. And then in the numerator, you get the square root of 51, 3 times 17. And still a plus or minus right there, equals x plus 2. And then subtract 2. And like I said, whoops, you get, not a real nice form for this, but it's okay. And so those are our x-intercepts in this case, are at -2 plus the square root of 51 over 3, and -2 minus the square root of 51 over 3. 0 would be the y coordinate. And you could use a calculator to approximate those if you needed to. And then the y-intercept is easier because remember there you're just setting x equal to 0. And so in the very first equation, where you have f of x, remember that's our function, f of x equals -3x squared minus 12x plus 5. And so you're really just finding f of 0 for the y-intercept. You're putting 0 in for x. And you end up with 5. And so the y-intercept's at 0, 5. So the y-intercept's always going to be easier to find. All right. So we know that first degree, to kind of sum it up, we're talking about polynomial functions. So first degree polynomial functions are functions, first of all, they're linear functions. And they're functions in this form, f of x equals mx plus b, and their graphs are lines. Second degree polynomial functions are called quadratic functions. Those are functions that are, their general form is ax squared plus bx plus c. And those graphs are parabolas, but either open up or down. And so now our objective in the rest of Chapter 5, or a lot of the rest of Chapter 5, so in sections 5.2 through 5.5, is to look at degree higher than 2. So the degree is greater than or equal to 3, right? And look at those kinds of functions. All right. So there are some particular things that we're going to be after. So now these graphs are more complicated. I'm just going to say that right now. Graphs are typically more complicated. And so what we're going to start doing is talking about features of polynomial functions, graphs, where the degree is higher than 2, and then trying to figure out how to figure those things out. All right, so the first thing to talk about is the intercepts. All right, so we're talking about intercepts. And so a typical polynomial function, might have a graph that looks like this. Well, that's a typical old polynomial graph. And so the x-intercepts for a graph like this are the places where the graph crosses the x-axis. And that would be an x-intercept right there and an x-intercept right there. And how do you find x-intercepts? You go ahead and you set y equal to 0, right? So you set y equal to 0. Well, you remember what another name is for y is f of x. And so, if that's the function we're talking about here is f of x. So you're really setting f of x equal to 0 when you're finding the x-intercepts. So sometimes these x-intercepts are, you're also going to see, when you look at this statement, f of x equals 0, you're going to talk about zeros of a polynomial. Right, so zeros of a polynomial and the x-intercepts are not necessarily the same thing, but you find them the same way. Now, zeros for a polynomial come in several different flavors. They come in several different forms. Zeros can be rational numbers. So rational numbers would be like the fractions, 2/3, -1, 5/8, 0, right? Those are all numbers that are rational numbers. They can be irrational numbers. Those are the ones with square roots in them typically. So like plus or minus the square root of 3, or 1 plus or minus the square root of 5/2, things like that. And then you have the imaginary zeros. And those are the ones with i's in them, like 2 plus or minus 3i, or plus or minus 9i, things like that. So zeros for, how do you find zeros for a function? You find zeros the same way you find x-intercepts. You set y equal to 0. So you're setting f of x equal to 0 to find the zeros. And when they are rational or irrational, then you have x-intercepts. Those are places where you get a place where the graph crosses the x-axis. When you have imaginary zeros, you have no x-intercepts. There's no place to graph those, basically, one way to look at it. So you don't get an x-intercept for imaginary zeros. All right, so we're going to more and more start talking about zeros when we're dealing with polynomial functions. But if they're rational or irrational, then we're also talking about x-intercepts, places where the graph crosses the x-axis. Zeros are relatively easy to find if you've got if they're rational. Irrational ones are harder to find, and imaginary ones are harder to find. But we're gonna talk about finding all of those. All right. So now remember, we're talking about intercepts right here. Now this graph also has another intercept, and that's the y-intercept. And the y-intercept in the graph is this point right here. And to find the y-intercept, what do? We set x equal to 0. And in terms of function notation, we're trying to find f of 0. So those are going to be typically much easier to find than x-intercepts. And the graph can only have one y-intercept because these are functions, and so it would fail the vertical line test if there was more than one y-intercept. One other thing to talk about with x-intercepts before we leave that we're going to have to discuss is the fact that if you look at those two graphs, you have what we might call a crossing intercept right here, this first one. When I say it's a crossing intercept, it means the graph actually crosses through the x-axis. And this other one is called a tangent x-intercept, or just a tangent intercept, in that the graph actually just touches. Sometimes you'll see somebody refer to it as a touching intercept, because it just touches the x-axis but actually stays on the same side. What I'd like you to look at there is that one of them kind of looks like a line and the other one kind of looks like a parabola. I say kind of because neither one is a line or a parabola, but they kind of remind you of that, and that will be something that we'll talk about, is how you find that information out about those intercepts, about the x-intercepts. All right, so that's what we need to be doing with intercepts. So we'll be talking about that. Okay, so let me put a box around that. That's intercepts. The next thing I want to talk about, things that we need to be worried about with polynomial functions, is something we call the turning points of the graph. So let's say we have a graph that looks like this one right here. Now, a turning point on a graph is a place where the graph changes from a rising graph to a falling graph, and these are called turning points for the graph. And so this graph that I've just sketched here has 3 turning points. You might also say it's a high or a low point on the graph. A high or low point on the graph. That's another way to look at it as far as a turning point. It's a place where the graph goes from falling to rising or rising to falling. And this graph has 3 turning points. It has two that are maximums and one that's a minimum. So these points here are all referred to as turning points. And so notice this particular graph has 3 turning points. This graph has 3 turning points. And this is a fact right now that I'm going to state about polynomial functions. And so we're going to write this out. Fact. A polynomial function of degree n can have at most n minus 1 turning points. We're definitely not going to prove that. We're going to use that as a fact here, that the most turning points it can have is 1 less than the degree. So a 4th degree polynomial, for example. So a 4th degree polynomial at most 3 turning points. It means it could have fewer turning points than 3, but at most it can have is 3. All right, a 5th degree polynomial can have at most 4 turning points. So a 1st degree polynomial, if you think about it, this makes sense. A 1st degree polynomial, which is our linear function, right? It's a line. It can have at most 0 turning points. And that makes sense because a line doesn't have any turning points. And so 0 makes sense in this context. All right, so that's something that we will want to talk about is, now we're not going to be as precise as a calculus student would be about those turning points, but we are going to want to know how many there are in a problem and where they are approximately at the very least. Okay, so turning points is something that we're going to be after as we deal with polynomial functions. So intercepts and turning points. All right, and notice the turning points have a lot to do with the degree of the polynomial. All right, and then the next thing we want to talk about is what we call the end behavior for a for a polynomial function. So the end behavior. The end behavior is something that we will want to know for a polynomial function. So the end behavior, what I'm talking about with the end behavior of a polynomial function is this. If you have a graph that looks like this one right here, the end behavior is basically what the graph is doing on the ends of the graph, so to speak, away from the intercepts. So the end behavior has to do with what is the graph doing over here, and that is as x is getting big, as x is going to infinity, we're moving off in this direction on the x-axis, like this. We're moving off to the right. So we're moving off to the right here. And then what happens, same thing, same kind of question, but in the opposite direction. What happens as we're moving off to the left in this direction, and what is the graph doing over there, right? That's what we call the end behavior of the function. And we're going to go ahead and talk about this right now and discuss how to deal with the end behavior. Now, when the graph is moving off to the right, you're talking about, oh yeah, I've already got it written here, that you're talking about x going to positive infinity right here. And as x is going to the left, you're talking about x going to negative infinity right here. And basically, you're just asking, what is y doing in both of those, in those cases? What's the y value doing as you're moving off to the right and off to the left? And so as you're moving off to the right, the y value, in other words, f of x, is just getting big because the graph is going up infinitely far, and so y is going to infinity. Or you might see it written as f of x goes to infinity. And so this end behavior off to the right might be written this way: as x goes to infinity. In other words, it's moving off, as you're moving off to the right on the graph is going up. And so f of x is going to infinity also. And you're just simply saying it's moving up when you're saying that. In the other direction, what's happening there? As x goes to negative infinity, in other words, you're moving off to the left on the graph, then what's the graph doing as you're moving off to the left? Well, it's going up also. And so f of x is going to infinity here. That means you're moving up in that direction also. Now in a picture, in a very brief picture, I might just write it like this too. That in the end behavior of this particular graph is rising off to the right as we're going to the right, and it's rising in this direction as you're going off to the left like that. So you could actually just draw it out very briefly like that to describe it that way. All right, so let's look at a couple of graphs and talk about their end behavior and how that works. And then we're going to talk about actually how you can look at a polynomial function and decide the end behavior of the function. So in this next graph, let's say we have a graph that looks like this one. All right, so the end behavior of the graph, right, if we just shade, that's the piece we're looking at as we go off to the left, and this is the piece we're looking at as we go off to the right like this. So if we write this out, if we're going off to the left, we're talking about as x goes to negative infinity. What is y doing, or f of x? Remember, it's the same thing. Well, the graph's going up, right? So f of x is going to infinity also. You're just saying that remember, you're just saying that the graph is going up as you go off to the left like that. And as you're going off to the right, now you're saying as x goes to positive infinity, as x gets to be a bigger and bigger number. But in this case, what's the graph doing? Now the graph is going down. And so we say that f of x is going to negative infinity. And that's just simply saying that the graph is going down, like that. And I could briefly summarize this this way, is I could draw out a little coordinate system like this and simply say that this graph is, as you're moving off to the left, is rising, and as you're moving off to the right, the graph's falling. But that's our end behavior. You could summarize it that way. All right. Let's look at one more graph, and then we'll actually talk about how you can take an equation and write out the end behavior for that equation. Let's say we have this graph. All right, so let's say we have a polynomial graph that looks like this one right here. And so hopefully, if you're watching this video at home, you're kind of thinking to yourself already before I say anything what the end behavior of this graph is. Right? We're talking about to the left that piece of the graph and to the right this part of the graph like this. So what do we have here? As if you're moving to the left, as x goes to negative infinity, then y, which is f of x, is graph's falling as you're moving off to the left. So the y is going to negative infinity. Y is just going to be a bigger and bigger negative number. Right? That means that the graph is falling or going down as you're going in that direction. And as you're moving off to the right, so in other words, as x goes to positive infinity, f of x, well, again, the graph is going down. So this would be negative infinity also. The graph is moving down that way also. All right, so that's a kind of a brief introduction to the end behavior. So these are the things that we're going to be talking about for a function in general. We want to be talking, as we go back through some of the things we've just discussed, we want to be able to deal with the end behavior of a polynomial function. How do you find the end behavior? We want to talk some about the turning points. And we also want to find the zeros for the polynomial function and the in particular the x-intercepts, the zeros that give us x-intercepts. And we also want to be able to find the y-intercepts. So that's kind of a rundown of the major things that we're going to be talking about as we're dealing with the graph of a polynomial function. All right, so we've got a sense for the end behavior as far as looking at a graph. So the question is, how do we find end behavior given the equation for a polynomial function? All right, and so to do that, you need two things to be able to figure it out. You need the degree of the polynomial function. We need the degree, so we need to talk about that. Be nice if I wrote it out correctly here. We need to find the degree and the leading coefficient. If we can find those two things, then we can figure out the end behavior for any polynomial function. And it turns out that generally speaking, the degree and the leading coefficient are not hard to find out. All right, so in a polynomial function written like this, 2x cubed minus 3x squared plus 6x minus 8, the degree is simply the exponent on the that's the biggest power on any of the x terms that you see in the equation. So you got to have terms. It's got to be all written out as addition and subtraction. You can't have any factors in there. And once you've got it written out in terms, then you're just picking up the biggest power on x. So the degree of this polynomial, that's easy. That's 3. And then the leading coefficient is simply the coefficient of the term with the biggest power. So the leading coefficient, and by the way, I'm going to frequently abbreviate leading coefficient just with the words LC, is simply the coefficient of the term with the biggest power on x. All right, so the leading coefficient in our problem here would be equal to 2, positive 2. All right, so this is a third degree polynomial, and the leading coefficient is 2. So the end behavior, what we do is what I want you to think about is f of x equals x squared, and think about f of x equals x cubed. And with x squared, right, that's an even degree function. That's even degree. X cubed, that's odd degree. Well, it turns out that all even degree polynomials kind of, as far as their end behaviors, kind of match up with x squared, and all odd degree polynomials kind of match up with x cubed. And so this is what I'm talking about. What is x squared? What does its end behavior look like? Right, there's a x squared like that, and the end behavior is that as x goes to infinity, f of x goes to infinity, and as x goes to negative infinity, f of x also goes to infinity. Or you could abbreviate that just with this little coordinate system that I've been sketching, and you got that the graph looks like that. It's rising to the left and rising to the right. Well, it turns out all even degree polynomial functions have that kind of end behavior, or, because this is f of x equals x squared right here, or they have the end behavior of f of x equals negative x squared. And f of x equals negative x squared is simply the exact same graph, except it is turned upside down, right? It's a reflection. And so what is the end behavior there going to look like? It would just be flipped over. And so the graph would be falling to the right and falling to the left. All even degree polynomial functions have one of those two end behaviors. Odd degree polynomial functions, well, those go along with f of x equals x cubed. So f of x equals x cubed, or f of x equals negative x cubed. And so let's look at those two end behaviors here. So for f of x equals x cubed, we know the graph kind of looks like this. And so its end behavior is that as x goes to infinity, f of x it's going up, it's going to infinity. And as x goes to negative infinity, as you're going to the left, f of x goes to negative infinity. It's going down. Or, if we abbreviate it with our little coordinate system here, the graph is falling as you go to the left and rising as you go to the right. That's our end behavior. And with negative x cubed, what's happening there is just flipped upside down, right? The x cubed function kind of flips like that. And so abbreviating that end behavior, what would you have? That the graph, as you're moving off to the left, the graph is rising, and as you're moving to the right, the graph is falling like that. Well, basically all polynomial functions have one of those four end behaviors. And how do you distinguish? You look at whether the degree of the polynomial is even or odd, and you look at the leading coefficient, right? So, and if the leading coefficient is positive, it's the first one of those in each of those groups. And if the leading coefficient is negative, it's the second one in each of those groups down there. And so for our function right here, given, this is our third degree polynomial function, right? What do we have here? We have an odd degree function, positive leading coefficient, right? This one is odd degree, that's because it's a odd, degree 3, leading coefficient is positive. And so those two things together mean that this end behavior for this graph looks like x cubed. It's an odd degree function, positive leading coefficient, and so the graph would be falling as you go to the left and rising as you go to the right. Or you might see it written out, that as x goes to infinity, in other words, going to the right, f of x is going to infinity. And as x goes to the left, it goes to negative infinity. F of x goes to negative infinity, like that. All right. On WebAssign, they may have questions where you have to answer it in that way. So you just have to be careful. All right. So we're on our way. So we started talking about end behavior and how to find it from the function. All right. By the way, this summary at the bottom of this screen is sometimes called the leading coefficient test, just so you know. So this is sometimes called the leading coefficient test. So if you see that referred to in a book, that's what they're talking about. Leading coefficient test is a way of deciding what the end behavior of a polynomial function is based on the degree of the function and the leading coefficient. All right, so let's look at another example. F of x equals negative 2x to the fourth minus 3x cubed plus 6x minus 8. All right, so this polynomial function is also written out as terms, right? It's all addition and subtraction. There's no multiplication, no factors anywhere. So the degree for this function is 4. That's the x with the biggest power on it. The leading coefficient is the coefficient of the fourth degree term, and so that is negative 2. And so what do we have here? We have an even degree polynomial function. That means it looks like x squared as far as its end behavior goes. So that means its end behavior is either going to be the parabola opening up like that, or it's going to be the parabola opening down like this. And because the leading coefficient is negative, which one do we have? We have the second one. It's been flipped upside down, and that's our that's our end behavior for this function. That this graph is falling as you move to the left, and it's falling as you move to the right. Or again, and I'll try to write it both ways, as x is going to infinity, f of x is going to negative infinity, it's going down. That's the right, moving to the right. And that as x is going to negative infinity, in other words, you're going to the left, the x value is going to be a bigger and bigger negative number. F of x is also going to negative infinity. All right, you'll see it written that way. So that's that's the end behavior for this function. Okay, so that's all looking not bad at all. And my experience has been that most students get the leading coefficient test without too much problem at all. And on your next exam, when we look at some polynomial functions, these are going to be the first 3 things I'm going to ask you to find. I'm going to ask you to find the degree of the polynomial, the leading coefficient of the polynomial, and what its end behavior is. Those are the first 3 things I will always ask you to find about a polynomial function. All right. Let's look at this function now. Let's say we have f of x equals x plus 2 times x minus 3 times x minus 5 times 3x minus 4. All right, so now this polynomial function is written out in a different form than the first couple that we looked at, because now it's written out in factored form. And so what you have to do is think about what's the biggest power of x you can get if you multiplied this out. What is the biggest power of x? When multiplied out. That's what you have to think about. And really, to do that, all you're doing is just simply taking the degree of each factor and adding them together, because this is the way this is going to work. Think about this for a second. If you take a couple ways to think through this, but if you took these 2 factors and multiplied them together, the x plus 2 times the x minus 3 using FOIL, you'd end up with an x squared in there somewhere. And then that x squared times that x in that factor would give you an x cubed. And then that x cubed and the x in that factor, when you multiply them together, you'd end up with an x to the 4th. And, if you think about it, all you're really doing is looking at the degree of each of those factors. The degree of each of the factors individually is a 1, because it's all x to the 1st in each one of them. And so when you add those together, you get 4. So either way you think about it, you get the degree of this function to be 4. So it's a 4th degree polynomial. The next thing is what the leading coefficient is. So you look at the coefficients of all the x's. And so the leading coefficient, if you think about this for a second, you've got the x in the first term, the x in the second term, the x in the, or I'm sorry, not terms, the factors, the x in the first factor, the x in the second factor, the x in the third factor, and then the 3x in the fourth factor. And that ends up giving you 3x to the fourth. So the leading coefficient is going to end up being 3. And so then what's our end behavior going to be for this function? Well, it's an even degree function. Leading coefficient is positive, right? That's what you're looking at. Even degree function, positive leading coefficient. And putting those two things together, we get that this graph has an end behavior that looks like our square function. And so that would mean rising as you move to the left and rising as you move to the right. Or, if you want to write it out, that you could say that as x goes to positive infinity, in other words, moves to the right, f of x goes to positive infinity. In other words, the graph's going up. The y values are getting bigger. As x goes to negative infinity, in other words, you're moving to the left, f of x is also going up. You're going to infinity that way also. Or, the y value is getting bigger and bigger. All right, so let's see. Let's look at the next example. So let's say we have f of x is equal to x plus 3 times 2x minus 1 cubed times x squared minus 10. All right, so this is a little bit more complicated as far as finding the degree of this expression. So now, or this function. The degree of this first factor is a 1. The degree of the second factor, since that's cubed, the degree of that factor is going to be 3. Because you have that x on the inside of the parentheses, but it's going to be multiplied by itself 3 times. So you're going to end up with an x cubed. And then the degree of this factor is 2, because that's a x squared on the inside. And so the degree of this particular polynomial function ends up being 6. When you multiply everything out, you'd end up with an x to the 6th in there somewhere. The leading coefficient, also a little bit tricky to find. The leading coefficient here, well, you get an x to the first in this first factor, but in the second factor, you end up with a 2x cubed. Then you end up with just an x squared in the third factor there. But that 2x cubed means you end up with an 8x cubed. And so you end up with an 8x to the 6th, and our leading coefficient ends up being 8 in this problem. All right, so this one, once again, has an even degree, function. And the leading coefficient is positive. And so our end behavior is going to be rising as you go to the left and rising as you go to the right. Or writing it out in symbols, as x goes to the right, as x goes to infinity, f of x goes to infinity also. The y value is getting bigger and bigger. And as x goes to negative infinity, as x gets to be a bigger and bigger negative number, y, or f of x, also goes to infinity because the graph's getting bigger and bigger there also. All right, so there's our end behavior for that particular function. All right, so now we've kind of got the end behavior handled. So, that's a big step forward here on the problem. So let's see. Next thing is, let me give you a graph, and let's see if we can discuss the degree of this graph based on some of the things that we've talked about so far. All right, so let's say that our graph looks like this. Interesting, okay. So first of all, let's talk about whether the degree is even or odd a little bit. So we look at the end behavior of this graph. So the end behavior on the picture, we're just looking at those two pieces of the graph, those two features of the graph, and we see that as x goes to the right, the graph is dropping, so f of x goes to negative infinity. And as x goes to the left, f of x goes to positive infinity, because the graph is going up right there. Or you could certainly have just abbreviated the end behavior like this with our little coordinate system and told me that the end behavior is rising as you go to the left and falling as you go to the right, like that. So what does that tell us about the graph as far as whether the degree is even or about the function, whether the degree is even or odd? Well, that would tell us that the degree must be odd for that kind of behavior. So the degree is odd, and the leading coefficient must be negative, right? Because it's the cube function, but kind of flipped upside down. And then let's also get a grip here on the turning points. And so the turning points, how many turning points does this graph have? And so it has 1 turning point, 2 turning points, 3 turning points, 4 turning points. And so since it has 4 turning points, its degree must be 5 or bigger. So the degree, because there's 4 turning points, the degree has to be one more, at least one more than the number of turning points. So the degree is going to be equal to 5 or bigger. And so putting those two things together, the degree is odd, and the degree's got to be 5 or bigger, then we know that the degree for this function has to be 5, 7, 9, like that. We don't know if we don't have enough information to say which one of those it is, but it's either got to be 5, 7, or 9, so etc. It's got to be odd and 5 or bigger. All right, so it would be nice to be able to look at a graph and decide what the end behavior is, and then from that, be able to tell what the degree of the function has to be, or at least get some sense of what the degree of the function has to be. All right. So now, next thing we want to talk about here is, so we've talked about the end behavior, and we kind of have that nailed down. We've looked at the turning points and kind of used that as far as graphs go. So now let's talk about dealing with intercepts for a function and start talking about intercepts a little bit. So finding zeros and intercepts. All right, so finding zeros and intercepts for a polynomial function. And so first one we're going to look at is f of x equals x plus 3 times 2x minus 1 times x minus 5. All right, so let's practice a little bit with what we've just talked about. First of all, the degree for this polynomial function. You have 3 factors in there, all have x to the first, so the degree here would be 3. The leading coefficient, you have an x, a 2x, and an x, so you're going to end up with a 2x cubed, so the leading coefficient's 2, which means it's positive. And so putting those two things together, the end behavior we have an odd degree function with a positive leading coefficient. And so that means as you move to the left, the graph has to be falling, and as you move to the right, the graph has to be rising. It has to look like the cube function. In symbols, you'd be saying that as x goes to the right. As x goes to infinity, f of x is going to infinity. The y value is getting bigger. And as x is going to negative infinity, f of x is going to negative infinity also. As you move to the left, the y value is getting smaller. It's going down. It's getting to be a bigger and bigger negative number. All right, so now the zeros and the x-intercepts for this function. Whoops. So the zeros, we talked about that a few screens ago. What you get those by setting y equal to 0, right? You set y equal to 0. In other words, you set f of x equals 0. And so for our zeros for this function, we set f of x equals 0, and we get this equation. X plus 0 equals x plus 3 times 2x minus 1 times x minus 5. And notice that since it's factored, that's actually a very, very easy equation to solve because all you have to do, since it's multiplied to give 0, is you just simply set each factor equal to 0 and solve those equations. So you get x equals negative 3, x equals 1/2, and x equals 5. So the zeros for this function are simply negative 3, 1/2, and 5. Those are all rational zeros. Remember, rational zeros are the fractions. So negative 3, remember, is a fraction because it's negative 3 over 1. 5 is a fraction because it's 5 over 1. So these are all rational zeros. Those all give us x-intercepts also. So those are rational zeros. And so those give us x-intercepts. And so you've got the x-intercepts for this graph are the same as the zeros. It's just negative 3, 0, and 1/2, 0, and 5, 0. Like that. The y-intercepts for this function. Remember, the y-intercepts, you set x equals 0 in the equation. And so you get this equation, f of x, you get f of 0 to be 0 plus 3 times 2 times 0 minus 1 times 0 minus 5. So you get 3 times negative 1 times negative 5, and so you get a y, you get positive 15 right there. And so you have a y-intercept at 0, 15. All right, so kind of walking back through this, we used the leading coefficient test to find the degree and the leading coefficient, and then putting those two things together, that allowed us to write down the end behavior. All right, the next thing we did is we looked at the zeros for the function. And how do we get the zeros for the function? Well, what we do is we set y equal to 0. In other words, we set f of x equals 0. And if the equation is in a factored form like this one is here, then those are easy to find, and because you're just setting factors equal to 0. In this case, these were rational zeros. These were all fractions. And because these were rational zeros, you also got the x-intercepts, right? So we found the x-intercepts. And then finally, the y-intercept, right? How do we find the y-intercept? We set x equals 0. In other words, we look at f of 0, and it's just a matter of plugging in 0 for every place you see an x. So the y-intercept's usually going to be pretty easy to find. All right, so so that's walking through what we've been talking about with polynomial functions. Now, there's definitely complications to this that we need to talk about, or just different situations. I wouldn't necessarily say complications, but so let's say we have f of x is 3x minus 2 times x plus 1 times x minus 4 quantity squared. All right, so that's our next one. And we'll probably look at this problem in one, maybe one more, and then we'll be done. We kind of got a late start today because of the technology issues at the beginning, but so we'll look at this problem and one more, and then we'll be finished for the day. And we'll have gotten a lot done, definitely. So the degree for this polynomial function, right? You've got a first degree polynomial function, or a first degree factor, and another first degree factor, and then a second degree factor. So the degree for this polynomial will be 4. The leading coefficient, well, you've got a 3x, an x, and an x. You have a 3x, an x, and an x. And so that's just going to give you 3x to the 4th. So the leading coefficient is going to be positive 3. So the end behavior for this function, at the end here, putting those two things together, we have an even degree function. So it means it looks like the parabola x squared, and the leading coefficient is positive. So that means as you move to the left, the graph is rising, and as you move to the right, the graph is rising. Or in symbols, as x goes to infinity, f of x goes to infinity, and as x goes to negative infinity, f of x also goes to infinity. It's going up in both directions. All right. The next thing are the zeros for the function. And the zeros, we set f of x equal to 0, and we get this equation. And because this is factored, this is going to be an easy equation to solve. Now, we'll start talking next Monday, in next Monday's lecture, about what to do if the polynomial is not in factored form. But here all we have to do is set each factor equal to 0. Now notice that last factor, x minus 4, is squared. So technically, what you have here is that x minus 4 gets set equal to 0 twice. Now, from a practical standpoint, there's no real sense in doing that because you're going to get the same solution, but I do want to talk about that in a second. So the first equation, you get 2/3 as a solution. The second one, you get -1 as a solution. And in the last one, the last two there, you get x equals 4, obviously both times. So what we have here is that the zeros for this function are going to be 2/3, -1, and 4 occurs as a 0 twice. And so we say that the multiplicity of this 0 is 2. Now this is called the multiplicity of the 0 because it occurs 2 times. So this is a 0 of multiplicity 2. Right? So the multiplicity for a 0 is how many times a 0 happens. So since 4 happens twice in this problem, it's a 0 of multiplicity 2. Notice that ended up just being the degree of the factor. That there was just x minus 4 squared, so we ought to be able to tell that just from the exponent. The x-intercepts for this graph, well, because all of those zeros are rational zeros, those are all x-intercepts. So you have 2/3, -1, and 4. Whoa, I don't know what I'm writing here. Let's back up here. 2/3, 0, -1, 0, and 4, 0 are all x-intercepts. Now we'll talk next time about what that multiplicity does to the graph at that x-intercept, and it does change the way the graph looks, but that's something we will discuss next Monday's lecture. Finally, the y-intercept for this graph, you set x equal to 0, you're looking at f of 0, and so that's 3 times 0 minus 2 times 0 plus 1 times 0 minus 4 squared. Be careful, that's squared right there. So this is -2 times 1 times 16, because it's -4 squared. And so you end up with a y-intercept at 0, -32. All right, not uncommon for the y-intercepts to be pretty big for a function, even if the numbers are relatively small. All right, last problem I want to look at This will be the last one of the day. So we have f of x equals, let's say, x plus 4 times x squared plus 16 times x squared minus 2. All right, so there'll be a few things to discuss in this problem. And let's just go to the zeros on this one, and let's just talk about the zeros. Well, I tell you what, let's go ahead and do the whole thing. So the degree of this function, the degree of the first factor is 1, the degree of the second factor is 2, the degree of the third factor is 2. And so remember, you're just adding those degrees together. And so you end up with a degree of 5 for this function. The leading coefficient, all the x's are just have coefficients of 1, so the leading coefficient's a 1 here. And then the end behavior, finally, for this one is an odd degree function with a positive leading coefficient. And so this would look like our cube function, and so this graph would be falling as you go to the left and rising as you go to the right. All right, and so now the zeros, which is kind of the what I really wanted to talk about in this problem. The zeros, we set f of x equals 0, and we get this function, or this equation. And it's factored, so we're okay here. We just set each factor equal to 0. This is not a big deal. It's just that 2 of those equations end up being quadratic. Now, they end up being easy quadratics to solve, but they are quadratic. So this first solution is -4. So that's going to be a 0, and that's rational. And remember, since it's rational, it means you're going to get an x-intercept there. Now, x squared plus 16 equals 0. To solve that, use the square root method. So subtract 16, and then take the square root of both sides of the equation. But notice you get the square root of -16. You get imaginary solutions. And so these are imaginary zeros. And so no x-intercept in this case. Finally, the last factor is gives you this equation, x squared minus 2 equals 0. So you use the square root method here also. And when you take the square root of both sides, you get the plus or minus the square root of 2. Now, square root of 2 is that's a real number, right? It's not imaginary because it's the square root of a positive number. But this is what we call irrational zeros. But these do give us x-intercepts. All right, so what are our zeros for this function? Our zeros are going to end up being -4 plus or minus 4i, and plus or minus the square root of 2. The x-intercepts, the difference here is that -4 is rational. That gives us an x-intercept. Square root of 2 is irrational. You do get x-intercepts there also. So there's 2 more x-intercepts right there. Positive square root of 2, 0, and negative square root of 2, 0. The imaginary zeros do not give you any x-intercepts, so that's it as far as the intercepts go. And then the y-intercept, finally, I look at f of 0 in this problem, and I get 0 plus 4 times 0 plus 16 times 0 minus 2. And so you end up with, let's see, you end up with 4 times 16 times -2. 4 times 16 is 64, times -2 is -128. So you have a y-intercept at -128, like that. All right, so I think we're gonna call it quits at this point. The textbook homework, I'm going to continue to assign textbook homework. I don't pick this up, but this is good practice for you to be looking at. Certainly go back and look at 4.1 and 5.1. So please go back and look at those sections. But today we talked about section 5.2. And so the problems are on page 372 of your book, and this would be problems 13 through 37, odd. And also 47 and 47 through 53, yeah, 47 through 53 odd. And then if you're feeling particularly ambitious, you could look at section 5.3. We haven't quite finished 5.3 yet, but we've gotten through a decent amount of 5.3. And so you could look at page 390 and look at problems. I would look at problems 7 and 9 and 31. We definitely have more to do on that section than those problems. So, all right, so that finishes up what we're going to do today. We've covered, we reviewed 4.1 and 5.1. We covered 5.2, and we've started in on 5.3. We still have a little bit more left to do in 5.3 that we'll talk about next time. So next time we'll look at 5.3 and 5.4 and get those sections done. So next time, 5.3, finish, and 5.4, and that will take us up through next Monday. So please do not hesitate to come by my office for office hours. I'm kind of expanding my office hours a little bit in the evenings, just so you know. So let's see. So my office hours, today is October the 4th. These are online office hours. And I don't have too many people coming by, so it'd be nice to have people come by my online hours. So that's today from 8 to 9 p.m., so that's tonight. And tomorrow, so that's Thursday, from 11 to 12. And then Sunday, from 7:30 to 9. And for outside of test weeks from now on, my evening office hours are going to go like this. Evening office hours for most of the rest of the semester are going to be Sunday, 7:30 to 9, and then Monday, Tuesday, and Wednesday, 8 to 9. And so you'll get office hours. You know, there'll be 4 nights in a row there where I'll be available in the evening for office hours. So please don't hesitate to take advantage of those office hours, okay? All right, so that's it for the day. Amber, thanks for sitting and listening. For the rest of you who are watching this later on at home, let me know if you have any questions. Have a great day.